AB belongs to R and if R maps to R be defined by, a function is defined as fx equal to a cosine modulus of x cube minus x plus b mod x into sine modulus of x cube plus x. Then f is, we need to talk about the differentiability at x equal to 0 and x equal to 1. At the 2 points x equal to 0 and 1, we need to say about the differentiability. Now first of all, if we closely see this function, we know that cos is an even function, right? Cos x is an even function. So since cos x is an even function, so cosine of mod x will be same as cos x only, because cos is an even function. Okay. So the first one we can directly write as fx is equal to a cosine. Here this modulus is redundant. We can get rid of the modulus. Cos of x cube minus x plus b into mod x into here inside, if you factorize, it will be sine of mod x into x square plus 1. Okay. So it will be a cosine x cube plus x plus b into mod x into sine x square plus 1 factor we can take out of the modulus because it is positive, mod x into x square plus 1. Now if you see that x cube minus x, this is always differentiable because it is a cubic polynomial, and outside we have cosine x, that is also always differentiable. So cos of x cube minus x is always differentiable for every real values of x. So this function is differentiable. This is differentiable for all x belongs to R. What about this function? This function mod x. Mod x is non-differentiable. Mod x is non-differentiable at x equal to 0. And this function will be non-differentiable due to the presence of mod x. So that is also non-differentiable at x equal to 0. Right? So this function is non-differentiable at x equal to 0 and this function is also non-differentiable at x equal to 0. But since we are multiplying them, then we cannot immediately say that they will be differentiable or non-differentiable. We need to test for that at x equal to 0. So we can easily see that the non-differentiability can only appear at x equal to 0. Right. So we can straightforward go with option B, that is differentiable at x equal to 1, because in any situation this function will be differentiable at x equal to 1. So option B is correct, and non-differentiable at x equal to 1 situation will never arise at all. So option D is definitely false. Now let us talk about at x equal to 0. At x equal to 0, let me concentrate on this function. Okay, because this is always differentiable. So let me concentrate on this function. That is, let us say gx is equal to mod x into sine of mod x into x square plus 1. Let us check the differentiability at x equal to 0. Okay, it is continuous function at x equal to 0. So let us check for LHT at x equal to 0. So that will be limit h tends to 0 f of 0 minus h. Actually we are calculating for g. So it will be g of 0 minus h minus g0 divided by minus h. This is the LHT. So if we simplify, if we put in the function, it will be limit h tends to 0 g of minus h. Let us put minus h here. So it will be mod of minus h, that is h into sine of mod of minus h, that is h into h square plus 1 divided by minus h. So h cancels. And here we can put h equal to 0, so it will be 0. Right? So LHT is equal to 0. And what about RHT? RHT, right hand derivative at x equal to 0 will be limit h tends to 0, g of 0 plus h minus g0 by h. So that will be equal to limit h tends to 0, h sine of h into h square plus 1 divided by h. So again this h cancels and this sine factor is tending to 0. So clearly you can see LHT is equal to RHT at x equal to 0. So it is differentiable at x equal to 0. So this function is differentiable. This is differentiable at x equal to 0. And this is always differentiable. So the sum is always differentiable at x equal to 0. Or we can entirely say that this function is differentiable for every x belongs to R. So non-differentiability will never arise, and differentiable at x equal to 0 will occur in any condition. So option A is correct.